Hello everyone. Today, I am going to talk about design tricks for automotive BLDC motor from magnetic sensor view. This webinar will begin with an introduction to our company, followed by application example of brushless DC motor applications, common problems in brushless DC motor designs, and examples of how these challenges can be addressed with sensor ingenuity. After that, we will introduce our new ZCL Hall Effect IC and discuss the advantages of using ZCL Hall Effect IC. First of all, I would like to briefly introduce you to our ABLIC Incorporated. We, ABLIC Incorporated, are a specialized analog semiconductor manufacturer. We provide semiconductor products and solutions based on our vision of the 3S. We are working to create a greener and more comfortable society through small, smart, simple, that means more compact, energy-saving and easy-to-use products and solutions. The 3S come from our historical background. We started R&D of CMOS ICs over 50 years ago, in 1968, as a division of Watches Manufacturing Company. We started out manufacturing analog quartz ICs for watches and have since developed and manufactured a variety of semiconductor products. We began offering products for the automotive market in the late 1990s, and in 2003, we began selling products specifically for automotive applications. Subsequently, the semiconductor division was spun off as an independent company and changed its name to ABLIC Incorporated in 2018, and in April of 2020, we became a member of the Minabe Group. Now let's go to main topics. As many of you know, brushless DC motors were first used in automobiles with motors that run for a long time. They were first used in motors that operate for about the same amount of time as the car is running, such as radiator fans, air conditioning motors, and EPS motors. It has been expanded to include wiper motors and motors to control various engine timing. In recent years, sliding doors and window operations have been introduced. Brushless DC motors are now used in such a various application, but as their range of use expands, motor engineers are faced with a variety of challenges. One is temperature. To begin with, cars must be used in cold to hot environments, and motors are often placed close to the parts of the car that need to be cooled. In addition, to improve fuel efficiency, hydraulic control is increasingly being converted to electric control, and the motor is being placed closer to the heat source. Of course, the motor itself also generates heat as it works. How to control this heat generation and keep it within the operation temperature range of various parts? Everyone has a very hard work, I know. Second one is the tolerance. Engineers are trying to figure out how to achieve target performance within size constraints. Also, a more efficient motor will ultimately reduce the amount of material used, which can save its cost. While you want to achieve a more compact and precise motor, the reality is that a motor is made up of many parts, and the tolerances of individual parts and manufacturing tolerances cannot be ignored. Third one is the sensor placement. As you can see in the illustration, it would be nice if the PCB area is large enough to place the sensor in an ideal position, but in reality, a lot of electronic parts need to be mounted in a limited area. There are disagreements among the members of the development team about which constraints to prioritize. The fourth one is the IPM rotor type motor, which does not produce a clean sine wave of magnetic flux due to its structure. In many cases, as shown in this illustration, a sensor magnet is placed on the shaft and controlled by the magnetic flux. However, installing a sensor magnet is a burden in terms of both size and cost. I'm sure you had some points that you can relate to. Some of these issues can be solved by improving the use of sensors, Hall Effect ICs. The first is a proposal for a solution to the wide operating temperature range of the motor. Unfortunately, the ambient temperature of the motor and the heat generation by motor work cannot be managed by the sensor. Therefore, I introduce you how to prevent the temperature rise around the sensor as much as possible. One way is to move the sensor location as far away from the stator as possible. This is a technique to keep the distance from the stator coil, which is the main source of heat in the motor, and thus reduce the temperature rise. For example, in the case of the inner rotor type as shown in the illustration, it is better to install it as close to the axis as possible. The second is to ensure air flow around the sensor. This method is to take advantage of the air flow induced by the rotor by avoiding the installation of high components around the sensor that would impede the air flow. If these solutions do not solve problem, the last solution is to mount the sensor on the back side of the PCB. It is obviously better to be as close to the rotor as possible to sense the magnetic flux of the rotor more efficiently, but if the operating conditions cannot be met, the sensor can be mounted on the back side of the PCB to ensure that it is far enough away from the heat source. The second one is a proposed solution to the problem of uneven sensor position. The sensors detect the magnitude of the magnetic flux of the rotor and then output a signal. In order for each sensor to receive equal magnitude of the magnetic flux of the rotor, it is recommended to place them on the same circumference as possible. The position of the sensor on PCB is also affected by accuracy of chip mounter or misalignment of the component during solder reflow. To reduce these effects, the sensor should be positioned so that the Y-direction extension of the package faces the center of the rotor axis. When the solder resolidifies, it mainly moves in the direction in which the terminals are coming out, so this arrangement makes it less likely to cause angular misalignment. In the case of the SOT23 Type 3-pin package, commonly used in sensors, the more strongly pulled towards the two-terminal side during resolidification than one-terminal side. In summary, we recommend aligning the direction of the three sensor terminals and placing the two terminal side edges in the direction where the magnetic flux of the rotor is greater. By doing this, you will be able to manufacture brushless DC motors more accurately and stably. By the way, you may have noticed that there are still some unsolved problems. To solve them, we are introducing our new product, ZCL Hall Effect IC S57TZ. This ZCL detection method was developed for Hall Effect IC for rotor position detection in brushless DC motors. The S57TZ series is a ZCL Hall Effect IC aimed at automotive applications which can operate in a temperature range of up to 150 degrees Celsius. Thinner packages to support thinner motors, which are required to make the best use of limited space in the automobile. And it has features and characteristics that are fully considered to be utilized in automotive motors. Now, let's see how you are facing the challenges. This is a heat problem of the motor, which I talked. Keeping the distance from the heat source and the airflow are the key points for thermal management. Therefore, the Automotive ZCL Hall Effect IC S57TZ was designed with thin packages. We provide two types of package. One is the TSOT233S package with a maximum thickness of 0.8 mm, which is now widely used, maintaining the footprint and going reed shape of the SOT233 package, but making it extremely thin. The other is a non-lead type HSND6-2025 package with a maximum thickness of 0.5 mm, which has a flat lead shape but the lead protrudes from the side of the package and can be used with automatic visual inspection equipment to check the solder joint. These allow for greater distance and air flow from the heat source than in the past. You can also reduce the distance between the PCB and the rotor if the heating is not an issue, contributing to the miniaturization of the motor. By the way, all I've talked about so far is how to deal with heat generation at high temperatures. To properly control a brushless DC motor from low to high temperature, we had to consider the change in magnetic flux density that the sensor receives at each temperature. We provided solution by ZCL Hall Effect IC. ZCL Hall Effect IC detects when the S-pole of the applied magnetic flux density changes to N-pole or vice versa, that is when there is a polarity change, and switches the output signal. So, ZCL Hall Effect IC provides stable timing detection even if temperature of rotor magnet is changed. On the other hand, detection signal timing of conventional Hall Effect latch IC depends on magnitude of magnetic flux density, which is changed by temperature. ZCL Hall Effect IC makes it easier than ever to control an ideal motor over a wide temperature range. Then there is the challenge of variability in sensor position and location to be placed. As I mentioned, 4 points to make the behavior of each sensor more uniform, as shown here. However, with the ZCL Hall Effect IC, 3 of 4 do not necessarily need to be considered. As I shown on previous page, the ZCL Hall Effect IC switches its output at the right moment to cross 0 millitessera. This eliminates the need to align the magnitude of the magnetic flux received by each sensor. That is, it's not necessary to place them on the same circumference, to align the direction of the terminals, or to place the two terminal side in the direction of high magnetic flux. You can obtain a sufficiently accurate sensor output signal simply by orienting the package in such a way as not to cause angular misalignment. This also frees the sensor placement constraints. If you consider only the sensor position with respect to the angle, you can obtain same output no matter where it is placed on the radial extension, although it is limited to locations where sufficient magnetic flux can be obtained. Now, let's see what happens when you shift the sensor. This is an experiment to see how the power consumption of a brushless DC motor changes when only one sensor position is shifted. Normally, each sensor is placed on the same circumference, as in the left board. But in the right board, the sensor is shifted outward by about 2 mm from its normal position. Now take a look at the demo video on the right. The red propeller is a brushless DC motor running with the ZCL Hall Effect IC, and the blue propeller is a brushless DC motor running with traditional Hall Effect Latch IC. The top motor has a normal sensor layout, and the bottom motor has a built-in board with a displaced sensor. The power consumption of each motor is shown in the center of video. As you can see by comparing upper and lower motor, the normal and shift configurations, there is almost no difference in power consumption between the ones running with ZCL Hall Effect IC. Those operating with Hall Effect Latch IC have increased power consumption when the sensor position is shifted. Let's take a look at the last unsolved issue, the IPM motor. The left figure is a CAD drawing of a typical inner rotor type IPM motor. The gray area of the rotor is the magnet. By placing a ZCL Hall Effect IC avoiding there, you will be able to rotational detection of the rotor. That is, the yellow area. Depending on the size of the rotor and other factors, if the size constraint is quite limited, it is possible to combine inner and outer sensor placement. This solution allows you to downsize your motor and increase value of your motor by detecting the magnetic flux of the rotor directly, eliminating the previously required sensor magnet and the sensor PCB. This is a summary of today. I talked about the problems of automotive brushless DC motors, and how you can improve them with the help of sensors. High temperature operation, sensor position variation. And with ABLIC's new ZCL Hall Effect IC, your problems are about to get even better. Thin package ZCL detection method can help you solve your problems. Thank you for watching. Please subscribe to this channel and give us a thumbs up if you like.